Hello everyone, Mr. Minnick's my name, math is my game. I'm joined today by my second period class. They're pretty excited to look at this lesson. They'd like to start off by giving a shout out to Jonah Rosenglen and Louis Nante. Mr. Robert Haney Jr. III's mother for giving birth to him. And we'll probably have some more shout-outs later. So Chapter 5, Section 2, Polynomials, Linear Factors, and Zeros. It sounds kind of like the Wizard of Oz, lions and tigers and bears, oh my. I told the first period group that this lesson, half of it's easy, half of it's not. If you're good at factoring, if you understand that when you factor, that you can find quickly the x-intercepts, the zeros, the roots, the solutions. If you remember that from Chapter 4, Section 5, you'll be in good shape with this. If you know how to multiply things out with the FOIL method, you'll probably be in okay shape with this. If you know how to use the calculator and use graph trace, you'll probably be okay with this. So the content standards, that you don't need to write any of those down. The first paragraph, all they're saying is what we're going to say right here. Real big statement. We're going to say let p of x be a polynomial function. Let p of x be a polynomial function. So p of x is some polynomial function. We don't know what it is, okay? And we really couldn't care less what it is. But what we need to realize is that if q is a root of p of x, then here's a conditional statement, kind of like a theorem, and later on in the chapter, we'll talk about how this actually is a theorem. It's called the factor theorem. I think it's called the factor theorem, don't quote me on that. But p of x is some polynomial function. If q of x is a root of p of x, then some algebraic expression is a linear factor of p of x. $20 question. Anybody know what the linear factor would be if q is a root? X is a good start, but x isn't all of it. X-intercept is not bad, but that's not what we're looking for. F of x isn't what we're looking for. Let's take a trip down memory lane. Suppose we had x squared minus 5x minus 6. Suppose we took that and we factored that into x minus 6 times x plus 1. If we did all that, we would say that that particular thing, that particular expression, if we made it a function f of x, we would say that f of x has roots of 6 and negative 1. Anybody got it figured out now? What goes in the blank? Okay. Apparently that snow day made it like a Monday. Because 6 is a root of this function here, because 6 is a root, x minus 6 is a factor. Because negative 1 is a root, x plus 1 is a factor. So the question is, if q is a root of p of x, then what is a linear factor of p of x? There was a comment, I feel bad for not knowing. Well, the first period class couldn't figure it out either. Somebody did. Is it what? Is it p of x itself? No. It's going to be some kind of algebraic expression. Let me try to make it as clear as mud. Here's f of x, right? Here's f of x. Because 6 is a root of f of x, x minus 6 is a linear factor of f of x. So we're saying we have some polynomial function p of x. We're saying that q is a root of it. Because q is a root of it, what's a linear factor of it? Oh my gosh. I'm not going to fill it in. I'm not going to fill it in. I'll let somebody will figure it out. It's not 6. It's not x plus 1. It's not x minus 6. Huh? I highlighted all the stuff that's pertinent to it. It's the same thing. We're just changing a couple things. Instead of 6, we're using a Q. It's not that difficult. Instead of a P, we're using an F. What I'm saying is that this 6 right here, is the same thing as this Q right here. And so, consequently, this x minus 6 should be the same thing as what goes in here. Thank you, x minus q, x minus q. 3 weeks later, here we go. Remember when we said that the factor to the root is counterintuitive? Don't forget about that. The factor to the root is counterintuitive. The factor to the root is counterintuitive. Okay. Example. Where'd example 1 go? Oh, it's got to be down here somewhere. There it is. Example number 1. Oh, man. They want us to factor. Oh, my first period class didn't do this. They're probably going to say they don't know how to do that on the homework. What is factored form of x cubed minus 2x squared minus 15x? It's been a long time since we factored. We didn't do it since chapter 4. A whole chapter ago. It's been about 17 weeks, it feels like. When you factor, you should always try to find a GCF before you do anything first, before you do anything else. Is there a GCF that we could factor out of that expression? We could factor out, I heard x squared, just an x. We could factor out just an x. So the expression we're starting with is x cubed minus 2x squared minus 15x. Each one of those terms has an x in it, and the GCF we're factoring out is x. So when we do that, it's going to be x times something. That's going to leave an x squared minus 2x minus 15. So you might think to yourself, and Kyle Borelli, I'm going to give a shout out to him. Kyle Borelli always gets a kick out of it when I say self. But self, can I factor that any further? Can I factor that quadratic trinomial any further? Well, remember in chapter 4 when we factored? We asked ourselves, self, are there any factors of 15 that add up? Oh man, here it is. There's the phlegm. Gotta love it. Are there any factors of 15 that add up to negative 2? 5 and 3. Because the 15 is negative, the sign's got to be the opposite. Because it's a negative 2x, where should we put the negative? With the 5. So a minus 5 and a plus 3. And don't forget about the x out front. And so that's it. That's our answer. That is our answer. Not bad. I told you, 50% of this is easy. And the other 50%, well, not so much. So the next one, the guiding example, we could again factor out an x. It's x cubed minus x squared minus 12x. It's just like the one before it, right? Factor out an x. So it's x times x squared minus x minus 12. Does 12 have any factors that add up to negative 1? What are we going to go with, a 4 and a 3? Bless you. And the signs are going to be, so it's almost identical. Minus and plus, right? Okay. All right. Well, let's take a look at the next example and see what they got in store for us. Where'd it go? There it is. Problem 2. They want us to graph this thing and to find the zeros. They want us to graph this and to find the zeros. My graph paper, I don't know what happened with that graph paper. I don't like it. Get some better graph paper going on in here. Okay. So because x plus 2 is a linear factor, since x plus 2 is a linear factor, what can I say? What is a root. If we were a banker, we'd be out of work. Because x plus 2 is a linear factor, what's a root? Negative 2. So remember what that means, what a root is. A root is an x-intercept. It's a solution to the related equation. It is where the graph goes through the x-axis. So when I go to graph this thing, it's going to look something like that right there. Because x minus 1 is a linear factor, what's another root? 1 is another root. Another root is 1. And on the graph we can do that. Because x minus 3 is a linear factor, what's another root? 3 is another root. So the graph's going to go through those 3 points. So we saw how to use the calculator to find certain key points of a graph. Well, you can also use your brain. Did you know that? That last test that you all took, you could use your brain to answer those rather than relying solely on the calculator. What I mean by that is there was this thing called end behavior. How does the graph act on the far left side, on the far right side? Does the graph go up on the left and up on the right? Does the graph go downward on the left and upward on the right? Does the graph go downward on both ends? Does the graph have on it what I have on my shirt? Some up dog? What's up, dog? Oh, not much. How you doing? There you go, Josh. All right. How could we figure that out? The end behavior. There's got to be a way. We only need to know one term of the function. Anybody remember which term we need to know? The first, the second, the third, the fourth, the fifth, the last? The first one. All we need to know is the first term. So let me get some of this other stuff out of the way. The first term would be the result of multiplying x times x times x. X cubed. So the function I'm looking at is x cubed. And that has a positive leading coefficient. What does that mean? That the graph is going up on the right. Because it's a positive coefficient, the graph's going up on the right. And because the degree is odd, is the graph doing the same thing on the ends or the opposite thing on the ends? The opposite things, the opposite things. So the end behavior of this is down and up. And there's one more point that we probably could readily find, could quickly find, if we were smart enough. I don't like the S word. I really don't like the S word, so I'm sorry I even said that. If we thought about it enough, if we found the product of these numbers, if we found the product of those numbers, that would give us our last term. What is our last term going to be? Bueller. 2 times negative 1 times negative 3. Negative 6. Is it negative 6 or positive 6? It's going to be positive 6. And what does the constant of a polynomial tell us? The same thing as the b in a linear function. It's the y-intercept. So this graph would have a y-intercept of 1, 2, 3, 4, 5, 6, a y-intercept of 6. And I think we could probably start filling in some of the details, huh? They don't have to be Van Gogh or anything like that. But the graph's probably going to look something like that. I don't know how far or how far up or how far down the graph's going to go. You know, I'm probably a little sketchy about this part right here. About this part right here. Probably don't know how far down that is, but it doesn't matter. It doesn't matter. You all have graphing calculators before you. Let's take a look at this on the graph. X plus 2, x minus 1, x minus 3. We could put that in that form too. It's kind of cool. So on a fresh graph page, we have the group of x plus 2, x plus 2, and the group of x minus 1, and the group of x minus 3. I said the group of x minus 3, and there we go. Hey, we did pretty good. We did pretty good. Anybody ever go to Windham, Ohio? I don't know what it is about that place. I like it. I used to drive my car through there. That was the thing to do back in the day. On payday, you put gas in your car and you drove through Windham about 38 times until the cops pulled you over and said, "Get the heck out of here." You just kept on driving around Windham. That was the thing to do. The Circle K was not there. That was just a gas station, and some old dudes would come out and pump your gas. And the guy that owned it kind of looked like one of the Mario brothers. It was full serve. It was full serve. They'd pump your gas. Yeah. New Jersey, I think they have to pump your gas. There's a gas station in Newton Falls that'll pump your gas. The one on my end of town used to just be full serve, and they closed that one down. Yeah, it's kind of scary. It's kind of scary when you get to a gas station that's full serve and somebody's out there pumping your gas, and yeah. So don't get it twisted. We're not talking about Windham here, but we are talking about some relative locals. So even though there's a couple of my cousins in this school, actually I was watching the news, true story, I was watching the news and someone said cousin on the news. Relative local mins and maxes. Relative local mins and maxes. It's a very fancy name for these things. If we're talking about relative local mins, a relative local min is something like this thing right here. It's not an absolute minimum because the function goes up forever and it goes down forever, so it's not an absolute minimum. And if we're talking about relative local maxes, it's not an absolute maximum, but nonetheless the function does have a maximum at that particular point. And it's called a relative local min and a relative local max. So I think now would be a prudent time to see if we can't find those because our graph has them. In case you're wondering how you go about finding these, it's real simple. We're just going to use graph trace. That's it. Just graph trace. That's your best tool. Here we go. Menu, trace, graph trace. So notice it flashes to the y-intercept. I'm going to cursor over a little bit. And right away, I find my relative local maximum. Okay. On the homework tonight, you're probably saying to yourself, how can I do this because I don't have a TI Inspire to take home? The calculator will say maximum. It won't say it's a relative local, but it will say a maximum or minimum if you get to the minimum. Okay. So let's think about this. You don't own your own TI Inspire. What other graphic utility could you use to get these? Mathway? I don't know if you would want to use Mathway or not. Desmos, sure. So if you're using Desmos, the beautiful free graphing calculator, check this out. Linear factor, x plus 2. Linear factor, x minus 1. Linear factor, x minus 3. And look at that. You just click right there. Got him. Click right there. Got him. There's your roots. There's that. What do you think? Am I against Desmos? Not at all. The only reason I don't encourage the use of Desmos during testing is because people would then use Mathway also. And that wouldn't be cool. So that's the only reason I don't suggest this. But for doing homework, I have no problem at all with Desmos. It's great. It's actually, I think, a little bit easier to use than the Inspire. So, yeah. Just punch in the equation and just hover and click. If you don't, you can click or just hover. Either way. Okay. Okay. So let's talk now about this. This is kind of cool. Multiply city. Multiply city. It's kind of a weird word. There's some words that come up in math class that you've probably never heard of. With respect to polynomials, multiplicity is simply repeated zeros. Repeated zeros. Okay. So we're going to look at a function, a polynomial function. F of x is x plus 4, the quantity squared, times x minus 3 times x minus 9, the quantity cubed. Now, I would be very impressed if somebody could tell me all the roots, all the x-intercepts, all the zeros of that function f of x. First of all, how many roots, how many x-intercepts, how many zeros should that function have?
3.
It shouldn't have 3. It shouldn't have 2. Let's think about standard form of this thing. If we were to multiply this out, and we were to find the product of the first terms, we would have an x squared times an x to the first times an x to the cubed. What would our first term be in standard form? X squared times x cubed. That would be x times x times x times x times x times x. Wouldn't it be x to the sixth? So there's supposed to be 6 zeros. Huh. Coats, my coats. So there's supposed to be 6 zeros. Well, it's pretty clear that one of them's -4, right? And it's probably also pretty clear that one of them's 3. And it's probably also clear that another one of them is 9. But it's not clear what the other ones are. Well, hold on a minute. Let's slow our roll here for a second. Let's think about if we expanded this, what it would look like. Wouldn't it look like this? Wouldn't it be x plus 4 times x plus 4 times x minus 3 times x minus 9 times x minus 9 times x minus 9? Wouldn't it be like that? Well, the fact that, where's my pointer at? Here we go. The fact that we have this factor of x plus 4 gives us that -4. The fact that we have this x minus 3 gives us that 3. The x minus 9 gives us the 9. So what are our other roots going to be? It's going to be a repeated -4. And then what? Another 9. And then another 9. So the deal is that function f of x has a 0 of -4, and that 0 has a multiplicity of 2. All multiplicity is a repeated 0. How many times it repeats? That function has an x-intercept, a root, a 0 of 9 with a multiplicity of? With a multiplicity of 3. Okay? So multiplicity simply says if a 0 repeats, how many times it repeats. An x-intercept of -4 with the multiplicity 2. An x-intercept of 9 with the multiplicity of 3. An x-intercept of 3 with a multiplicity of 1. If the multiplicity is 1, it's kind of not necessary to mention that. How's everybody feeling so far? So you're probably wondering or asking yourself, what does this mean as far as the graph is concerned? Well, I'll tell you, it has something to do with the golf course and going to a play. You're out on the golf course. You swing and you miss. And some words that come out of your mouth probably come out with great gusto. You're in a play, and you forgot to turn your cell phone off, and it rings, and you're the only person in there, and everybody knows that it's your phone ringing because it lights up, and everybody can see you. So you're going to spike it, and you're going to say, are you going to say anything? Okay. Well, I wouldn't say anything. No. I would apologize profusely. Yeah, and then probably make it matters worse. The point is, in theory, you'd probably behave differently in both situations, right? Well, the idea then is that the graph is probably going to behave differently in this situation than it is in this situation than it is in this situation. Do you understand what I'm saying here? When the exponent is 2, isn't that a quadratic function, a parabola, when the exponent's 2? So guess how the graph's going to behave near that point? It's going to behave like a parabola behaves. Oh, so you mean a parabola kind of turns around at that point. Well, yeah, that's what it does. So what I'm saying is that this graph, when you go to 1, 2, 3, 4, when you go all the way over here, the graph is going to behave like a parabola there. What I mean by that is it's either going to do something like this, or it's going to do something like this. But it is going to behave like a parabola at that point. Let's go to the other point, the 3. 1, 2, 3. How's the graph going to behave there? Like a line. How's the graph going to behave when we get to the, let's see, 4, 5, 6, 7, 8, 9. How's the graph going to behave out there? Like a third-degree polynomial. So let's look at a third-degree polynomial. Let's see how they behave, and then let's graph this, and let's see if this all makes sense. So on a new graphs page, welcome to the new page, a cubic function looks like that. Everybody kind of see how that cubic function behaves? So I get it. So the graph then should behave something like that. So the graph should do something like that there. Huh. Interesting. Well, there's probably some other information that I would need to know. Isn't there? Like what the graph does on the ends? What would this particular function do on the left and the right? The first term we said was x to the 6th. Positive, it's going to be going up on the right. Even, it's going to do the same thing on the ends. So what's the end behavior of this graph? Up and up. So the graph's probably going to look something like this over here. We said it's going to look like a line on the other side, so probably something like that there. And let's just graph it. Let's see what it looks like. Let's see what it looks like. So new page, doc, insert a graphs page. So we have x plus 4, the quantity. X plus 4, that quantity squared. I said that quantity squared, not squared squared. Times the quantity x minus 3 times the quantity x minus 9, the quantity cubed. And we'll graph it. Huh. You can see it kind of curves, yeah, around the 9. Let's do a zoom box on that. Or I'll just zoom in right there. I'll just do a zoom in right there. If I zoom in there, you can kind of tell, hey, it looks like a cubic function over there, doesn't it? Okay, menu, window zoom. Let me do a zoom standard now. It's pretty clear that the graph behaves like a line over there. But that negative 4, not so sure about that. Not so sure about that. Menu, zoom, data. Whoa. Menu, zoom, box. What's going on there? Does the graph look like a parabola there? It sure does. It sure does. Any questions? Does this idea of multiplicity make sense? Does the idea of how the graph behaves in a multiplicity make sense? I hope it does. All right. Are there any questions, comments, concerns, short debates, long debates, shout-outs? Shout out to the future Mr. Minnick. He's probably in the back taking notes. Or watching people on their phones. My 6th period group, there's usually only one person on his phone. Get off their phone, that person in 6th period who's always on their phone. He knows who he is. Problem number 3. What is a... Oh, no. This is where it starts getting a little bit more challenging. If you know how to distribute, if you know how to FOIL, this isn't so bad. They want a cubic polynomial function in standard form. The fact that they want it in standard form, this is what makes this one a little bit more difficult. We could start with this in factored form, and that's what I would recommend to do. Factored form first. Factored form first. Triple F. Not to be confused with Triple X. Did you see there's a new Triple X movie coming out? Xander Cage is back. It's about to be set off. It's going to be good. Here we go. F of x equals. Hey, wait a minute. -2 is one of the roots. What's that mean one of the factors is? Maybe we need to back that thing up. If q is a root, then x minus q is a factor. If q is a root, then x minus q is a factor. So if -2 is a root, then what's a factor? X plus 2. There we go. And we've got this 2 is also a root. So what's that mean a factor is? X minus 2. And then 3 is a root. So what's a factor? X minus 3. How are we doing? So we need to FOIL. I'll be frank with you, even though my name is not Frank. I think it's easier to multiply those two first than it is to multiply those two first. Does anybody understand why? Because they're both 2 and some stuff's going to cancel. So let's go ahead and do that. That's going to be x squared plus 2x minus 2x minus 4. That still needs to be multiplied by x minus 3. Canceling happens. We get x squared minus 4 times x minus 3. Now we can use the method approved by our social studies teacher. X cubed minus 3x squared minus 4x plus 12. Got him. Somebody asked a really good question the other day ago. Actually, today. You guys know that Angermeyer boy? Chad? He said, can the calculator do this? Here we go. Can the calculator do this? So I'm on a calculator page, and you could try this too. I'm going to type the word expand. I'm typing the word expand. And I'm going to have x plus 2. And I'm going to have x minus 2. And I'm going to have x minus 3. And I want to put a comma x. I want this to expand this around the variable x. Now, do you guys know Keenan Ivory Wayans? Keenan Rankin? Keenan Rankin owns a TI Inspire CAS, otherwise known as Darth Vader. Notice what calculator Mr. Minnick is using at the present time. The TI Inspire what? The CAS. Did you want to try that? Go ahead and press enter, see what happens on yours. It tells you that, you can't do it on yours, but I can do this on mine. So are you going to go out and buy a TI Inspire CAS? You can play Pokemon on all of them. I've got Fruit Ninja on my old calculator. Yeah. You swipe across the keys. You go like Zorro. Yeah. In case you're wondering, a TI Inspire CAS does not cost that much more than a regular TI Inspire. What you should be aware of is that this TI Inspire CAS is against the law in 48 states, especially Virginia. Virginia has a lot of laws. It's illegal. You're not allowed to use it on the ACT. You're not allowed to use it on the SAT. You're not allowed to use it on most college math class finals. It does all the algebra stuff that you're supposed to be able to do without it. The point of it is it's a great learning tool. if you're trying to check yourself before you wreck yourself. True story, anyone who is in possession of an Android device, you can, not that you will, but you can download for free an emulator of a TI-84, a TI-83, or a TI-89. The TI-89 is actually capable of doing a lot of those same things that the Inspire CAS can do. Okay. I actually have it. If you're interested in seeing how to do that, see me sometime after school or during my planning period, and I'll gladly show you how to go about that. Do I want to go to the new coffee shop? Perhaps one day. Today's not that day. Would you be able to multiply out something bigger than that? Or do we need to see one of those as an example? I think we got one more example, and then that's it. Yeah. One more example. Boy, there's a lot of them in the book, but I think if we just do this one last one, we'll be all right. We'll be all right. So here we go. This last one, a quartic polynomial. Oh, man. Coats my goats. Do they even say that anymore? I don't even know where that came from. I don't even know where that comes from. So here are the zeros. Here are the zeros. F of x would be x minus, no, not x minus 2x plus 2, and then x plus 2, and then x minus 2, and then x minus 3. What pair would should I multiply first? The first two, the last two, or the middle two? The middle two. Yeah, I'm going to go ahead and multiply those middle two because we just saw that a minute ago, didn't we? That's going to be x squared minus 4. Can I go ahead? Would it offend anybody if I FOILed out the first and the last ones and put that out front here? Would it offend anybody if I did that? Why do I not? Well, the commutative property of multiplication says it doesn't really matter what order I multiply these things in. So the reason that I wouldn't multiply the first two first is if I multiply the middle two first, I get some canceling, and there's one less term to work with. Okay, I don't know if that answers the question or not. There's more than one way to the Eastwood Mall, by the way, and Geauga Lake. So when I FOIL that first one with the last one, what's that going to be? X squared. How about minus x minus 6? Right? Yeah, x squared minus x minus 6. Okay. Good. Well, now I need to distribute this x squared to all three of those. So that's x cubed minus, no, that's x to the 4th minus x cubed minus 6x squared. Similarly, I need to distribute the negative 4 to all three. Oh man, that's negative 4x squared plus 4x plus 24. So my final answer would be x to the 4th minus x to the cubed minus 10x squared plus 4x. I said plus 4x plus 24. Wow. I told you some of this is really easy, some of it's really difficult. What do you think? So the graphing stuff, use Desmos. The stuff that you got to multiply, be careful when you multiply. Watch your signs. That's all I got. Any other shout outs before we call it quits? Shout out to the boys basketball team for beating Wyndham. A shout out to Mrs. Guy for getting Teacher Educator of the Month. Shout out to Josh's father. Shout out to Avery's mom. And a shout out to Ms. Sinisvet's mom. And how about the entire 6th period crew? It's been real, it's been fun. See you next time.